There will be a topic on the MySQL Optimizer. I will talk a bit about there have been some new things added to explain in the innovation releases 8.1, 8.2, 8.3, and I will just show something how you can use that. But to set the context, where we talk about explain as it has been before in 8.0 and many earlier releases, before I discuss the recent addition. And if there's time, I will do some touch up on explain, analyze, and optimize. So, how many have used explain here? Yeah, almost everyone, everything. So, and I guess all of you know what the query optimizer do. It takes, you have some text that is a SQL query. You run it to the optimizer. It uses information from data dictionary about the tables and indexes and column names and stuff. And then it uses statistics that says from storage engine, but also we have histograms which are collected by the server, not storage engine. And based on all this, it tried to find the best plan to execute this query. So in this example here, we have three tables, 2 joins, and you have some. So you do a range scan on the first one, and then you do lookups here, and you do a table scan on this one. And from the early days, what you got from explain is some tabular output where you basically have one row for each of the tables in the query. And you can see here which type of access method it chose for each table, which indexes were considered, and which one was picked. And there's an estimate for how many rows it expects to use of these of the ones that it's reading, and the number of rows it's actually reading. So in this case, it thinks will read 12 rows from T1, and it will use 1/3 of them. And then there's quite so often some extra information about the plan that does not fit in these columns. For example, in this case, it will push some condition down to the index. For example, if B is on T1, it can evaluate that if there's an index on both on B. And also in sometime 5.6 or 5.7, you also get the ability to explain a query from a different connection. So you can actually, if something is running for a long time, you can actually run explain on it and see why it, maybe what plan it has, and maybe understand why it takes so much time. Then later we added more versions of explain, different formats. The problem with this one is that it's kind of limited how much information you can put into a format like this. Also, many queries does not really have this linear type of structure, so you are not able to express kind of the entire plan in a good way. So we added JSON format. The main purpose here in this case was maybe to add more information that we didn't have. For example, you can see which columns are actually used by the query, and you can. One good thing is that you can see the conditions where they are evaluated. For example, in this case, you pushed an index condition down to the index, so you don't have to do lookups in the table if it doesn't satisfy this condition. And then you have conditions on the table after you get it back from the storage engine. I'll show one more example there. Here we have some pretty complex where clause, and the optimizer will want to, in this case there's a join and it starts with T1, reads a row from T1, then it does a lookup into T2. In this case, there's no index, so it uses another approach. You can see that this is actually not 8.0 because this one is not used anymore. So, sorry for the old slide. My point here is that when it has read a row from T1, it can apply as part of this condition. It can check and only select rows where A equals 9. But the rest of the condition has to be delayed until it has read from T2, where it can evaluate the rest. This explaining will actually show when the different conditions of the very close is evaluated. And another good thing about JSON format is that you can provide tools to actually analyze and read this the JSON document you get. With this explain, it's not very easy for a tool to pass this and produce something. So when we got introduced the format equal JSON, then Workbench was able to visualize the query plan. So you can actually see, in this case, you have 5 tables and you have a full table scan, and then you do different kind of index lookups on the different tables. But then in 8.0, we switched to a new query executor. The old one that's used in 5.7 earlier, it was kind of built on joins. So, and it represented then the tables involved as a table, which is internally in the code was called join tab. So you have a sequence of tables, and that's the join order you have. And then you annotate the different elements of the table with plan. The plan you have, like, you get an access type here is tables, all means table scan, ref means equality index of look up on an index on a value, and then you put the conditions on the different elements like this. And for nested joins, this work pretty well, but then you have, like when we introduce semi-join, for example, there are cases where you, let's say this is the subquery in the in expression of the semi-join. When you have evaluated, if you have a match on this one, you will normally go back and do the next row here, and then you like that. But in case of an in or exist expression, you actually, if you have found one, you are not interested in the next one, so you have to go back. So then you have to add pointers to actually how far back you have to go and things like that. So it doesn't really, it's not all type of queries are actually possible to express in that type of plan. And when you get hash join, it's also difficult because then you can have bushy plans where you have join 2 tables here and 2 tables here, and then you join those 2 results together and so on. That's not possible to express here. Another issue was that the code for one operation was kind of spread out all over the place, and not all combination would work. For example, if you have a ref access, you could not do sorting. You had to actually reroute that to a range access in order to apply sorting. So what we have changed to is the more modular, where every operation is what we call an iterator. So you have a table scan iterator, you have a filter iterator, and so on, nested loop iterator, and so on, and all have the same interfaces. So we can stack them in any order, and any iterator can take the input for any other iterator. So this makes it much more easy to extend to new execution strategies. And as I said, we can connect all these different operators.
That's not an exhaustive list of the operators. Right?
No, like you have a hash join operators, but this is a query plan where you actually have a table scan that on a filter iterator on top of a table scan iterator that goes into a nested loop join with another, and so on. And then you have another loop, and then you do an aggregation the temporary table, and then you scan this temporary table, sort the data, and then you put a limit on top, so you only present like 10 rows from that. But so the problem we have then, we have a new type of execution, but the explain did not no longer express all these different iterators and so on. So then we created a tree iterator, now tree explain. This is the same as the figure I showed on the previous slide, where we can actually see the structure of the whole execution plan. And this also has more information than the tabular explain, because you can we can annotate it with, and first you have filter as a separate step here, so you can see the different operation, and you see the conditions for this filter, and you have all the estimates here for how much, how many rows it thinks it will read on the different steps and so on. And, yeah, but it takes a bit of time to get used to reading this, because it's kind of inside. You have to kind of read it inside out to get the same ordering as you got in the old tabular explain. So I kind of switch between them. I mean, the old explain kind of give you a quick view of what's happening, but if you want the details, you can. This one tells you much more.
So the JSON output doesn't include like the filter as its own thing, right?
No, the old JSON, I'll put that, but the old JSON, let's see.
They have the attached condition there, right?
Just, no, this did not work, so I'll go with this one. Okay, so the old one, it didn't show it as separate, but you had the condition inside each table object. Let's see, let's go back to, and so then we could also add explain analyze. That with with this new iterator structure, adding timings when you actually execute the query is pretty simple, because you just put a timing iterator on every iterator here, and then you automatically get the can measure with this. They all have the same interface, so you can actually measure how much each step takes, and then there will be multiple calls here, and you can aggregate all the time it takes to do that. So then you can have explain analyze. I'll see if I get.
Sorry.
Yes.
Just have a 50% understanding of better what this model can do and cannot do. So can you do the operation, the operation around dependence, like doing the table scan, in one thread, at the same time we'll get the next step in another one, because they are let's say, different leaves.
No, there's no parallel execution here. It's like more details there. So each iterator class will have an init and a next function. So you call all init all the way down, and what every iterator will do on init is get to the point where it can deliver the first row. And then for this one, it's just to read the first row from the table. But for the sorting iterator, init actually means executing everything below and then sorting.
Yes, I mean, this is the point, for example, when you have the limit there. So when you are sorting, you need to sort everything before being able to limit.
Yes.
Let's say, you only have a table scan and you would like to limit. Does it mean that it will do still the full table scan and that only give you 10 first row, or it will be smart enough to say, I need only the 10 first, so I will...
Okay. Yeah, because if there's no step where you actually, when you call the next here, it will go down and do next on all these different ones, and then it had got 10 rows here, it will stop. So it will never be an 11th, or you don't know, but like, you will never have to read more rows than actually you need. They are pipeline, but they are, so you don't do it one at a time. You do one row at a time, you can say. So with explain, analyze, you can then you get the actual time it takes to get the first row and to get all, like if you look at the sorting up there is, to get the first row and then to get the other rows. And you get how many rows you have read, and then you have loops, means how many iterations you have. For example, if you look down here, which is on the line item, which will be the last table in the traditional sequential join order, you do primary key lookups. And each lookup takes on the average like 0.05 or something, 1 seconds, and then you get 4 rows from each lookup, but you do 145,000 such lookups. So the total time spent here will be this times this, I think, yeah.
So the time is per row? Or per loop?
Per invocation of this this operator. So that was the background for what we have added in the latest releases. We have added a new JSON format to better be able to express the new execution plan structure. So you can choose which one to use by setting the session variable explain JSON format version. So that's a comparison of the two JSON formats. So the old one, we have a less than loop array, and it has a set of elements that's one for each table, like the old traditional explain. So there will be, like if there's a 3-table join, there will be 3 different such elements inside the nested loop array. In the new one, it's a tree, and each iterator will have either 1 or 2 inputs in a normal case. So it's kind of harder to read for the human eye. But since the tree explain has so much more of this detailed information, you don't really need a JSON version just to get more details. But what we need a JSON version for is to be able to build tools to process the query plan. So here is an example of this object is an inner join. The nested loop inner join object, and which has 2 inputs: a filter iterator and a index lookup iterator. So in this case, there will be some kind of probably a table scan or an index range scan operation beyond that, but I have not shown the inputs for this operator. And you can also set your default explain output. You have an explain format variable, so you can set that to either traditional and get the old one. The tree one, this is just a single table scan, just to show the different kind of, or the JSON variant. You can also, with explain, specify the schema to use. Here's an example from, performance schema has this event statement summary by digest table. So we can use that to see the 3 queries in our systems that have used the most time. I order by some time await. So this is multiple executions of these queries have together used so much time. And these are the ones, as you can see, these are from my experiments for the presentation as I've done. But the point is that you have a sample query text, and then you have a schema line for the current schema when executing this query. And then if you have a tool, it's kind of cumbersome, then have to switch schema to get the query plan for this query. So one thing there I can mention is that in performance schema, you normalize the query. So in this case, for example, this second query, I have the country equal Canada. So that will be normalized to country equal something. And then you will aggregate statistics on all queries that looks like this, has different constants, but it's basically the same query. But then in order for us to be able to get a query plan, we need some data here. So what query performance schema has, it has this query sample text, which is an actual query that was used for this specific digest. And as far as I know, this sample text will be refreshed by, but it's not necessarily the latest one that was executed, but it will be refreshed with some time interval. So then I can just take the schema name from the performance schema table and use that as explain for schema, import DB, and then I can actually just paste the query that they have there, or in case if you have a tool, you have read these columns and you can then you can present the query plans for different queries. But note that the plan you get here is not necessarily the same for all queries with the same digest. Because if there's a country with few entries into the passenger tables, it will probably could use an index on country, for example. But if this was United States, it might have to say, oh, there's so many, we can have to do a table scan instead. So what you get here is not necessarily the same plan that has been used for every query of this type.
If the query sample text is maybe truncated rather than the query sample text may be truncated,
yeah,
so you may not be able to use it exactly depending on the query's on.
Yeah, that's true. Also the digest text, I think the digest is on a limited size of the query. Yes.
Sorry, this is really about performance schema, not about this. Sorry.
Okay, we take it after. That's good. Okay, and we also have another thing that could be useful if you are creating a tool on processing explain plans with SQL, is that you can explain format JSON into some user variable. So then you can take this user variable and then you can run queries on your JSON plan. Note that you have to have this format equals JSON there, so it does. So even if you have set your default to JSON, this into does not work unless you specify it. Yeah.
Can you combine this with the JavaScript stored procedures to then analyze the JSON using a JavaScript?
Yes, you can.
Okay.
So that's probably better than doing this in SQL. But there's just an example where the first example here, I search for access type within this plan that contains the word limit using the JSON search functionality of SQL function. And if it's not null, that means that there is a limit on this query. There's a more complex example. I want to see, I'm looking for the orders the table name should be orders. And I want to see the part of the JSON document that describes this orders plan. It's kind of tricky here, but what I do is that I take what I get from I will get a path from JSON search, and that in that path I will replace table name with operation, which is the another attribute on the same object. So what I actually get then is this textual description that explain format equals 3 uses. So what happens to, we can see here that what happens to the orders table is that there's a index range scan on it using the I order date column. No index. So this is probably most of you will not have use for this. If you want to write a tool as it's either you can just read this the result of explain into JavaScript or to a client in some language and process is there. And JavaScript is very good for JSON processing. Or you can use the built-in JavaScript functions to process this. Okay, so that's the new additions on explain. Explain analyze is not. It was new in 8.0. So, but probably, how many have tried to use explain analyze? No? Some have?
Really useful.
Yeah, so I will just show an example of using it. So I have this queries from the TPCH benchmark, and you don't need to understand it in any way. You can note that there is a condition on the on this path table, and there is a subquery that will be executed multiple times for each in order to check this condition. And then run the explain analyze on it. And the first thing I notice is that so the estimate here is that there will be 3,555 rows in this query. But it says there was only 164. So that's an indication that probably there's something that's wrong here. Some estimates were wrong. And if I look closer at this, for example, this filter here, it estimates actually that 11% will actually satisfy this filter condition of those lookups you do into the path table. Turns out it's less than 1% that actually satisfies this. And the reason why the estimate is so bad is because currently we have put histograms on the P name, but the like operation is not currently supported. So then it just guesses, makes a guess here. It's some, actually it gets the same, yeah. So it has some guess that is 11% or the detail of how, but the real one is 0.092%. No, 0.9%. So, and also, we have this filter condition here that's actually a subquery. Select number 4 is the subquery where you see also there. And this subquery is executed 26,000 times. And from the order here we see that it reads the part subtable, executes the subquery, and then later it does this filtering. So maybe doing this filtering on path before executing this subquery would be better. So based on that idea, I use a hint and say that why don't you try to join on path before you join on path. So the join order of path to paths should be specified by that hint. And you see that has good effects. In this case it took 0.9 seconds without any hint, and it took 0.3 seconds with this hint. Yes, I don't think, do you have the explain analyze for the integer? And I can
can see.
You can take it afterwards, I think. I can show it to you, but
To see the loop,
we'll explain on it for the new function, yeah. No, I haven't I didn't add that, so, but that will
if
be
you
a
come up
good
here
idea.
later, it will. At the dinner, if you bring you a beer, you will show it.
Yeah. So, was there some questions?
If we look at that last mice output,
I'm trying to get back to it.
It's too late. Finished.
I went back, you know.
We got the problem.
Let's see. This one?
yeah. So in the filter, you said that 0.11 was percentage. But then above rows was actual number of rows.
Yeah, I said percentage because,
It's confusing.
yeah, it's confusing, but the point is there's 7,795 lookers into this table. And
And it returns one row.
yeah, and on average, each of these returns one row because it's a single row index lookup. It's a lookup on the primary key. So this is the average over all these 7,795 rows. On average, you get back 0.1 rows.
Makes sense.
Thank you, Øystein.